Hi, my name is Larry Wasserman. I'm an astronomer here at the Lowell Observatory in Flagstaff, Arizona. This is the second of these Meet an Astronomer talks I've given. The other one is somewhere out there on the web, on the Lowell website. And if you like this one, you could look for another one by me. I've been asked to do a small commercial. It turns out that this week is the fifth anniversary of the New Horizons flyby of Pluto. And Lowell Observatory, in addition to these Meet an Astronomer talks, does something called the Cosmic Coffee at 9 a.m. every Thursday. And this Thursday, it's going to be a talk with Gerard Van Bell, who was at the IAU meeting where Pluto was demoted from being a planet. He voted. And I'm going to talk about that also a bit later. And a week from that, Will Grundy, who's also an astronomer here at Lowell, is going to be talking about what have we learned from Pluto in the last 5 years. And he was a member, or is still a member, of the New Horizons science team. Okay, so that takes care of the commercial. And now we'll have to see why I can't advance this. Oh, why can't I advance my, there we go. All right. The Kuiper Belt is a large number of small bodies which orbit the sun beyond Neptune. It's estimated there are millions of these bodies, but together, they only accumulate about a tenth the mass of the Earth. The largest one of these is Pluto, which has a diameter of almost 1,500 miles. And the smallest, and of course the most numerous, are basically small rocks, so they don't count for much. And why can't I advance the slide? I see. And for this talk, I'm going to use the term Kuiper Belt to include objects that have been perturbed by Neptune into orbits that have their perihelia. Perihelia is the closest point to the sun, that are well inside the orbit of Neptune, and objects that have been perturbed by Neptune into orbits that have their aphelia, which is their furthest distance, well outside the orbit of Neptune. So the belt is quite wide because it includes objects that come well inside the orbit of Neptune and those that extend well beyond it. These objects seem to be pristine, mostly icy bodies left over from the origin of the solar system. And in a minute, I'll talk about this, but these objects seem to be the source of short period comets. Well, how did we find this thing in the first place? Well, in 1930, Pluto was discovered here at Lowell Observatory, and that indicated that there was something out there beyond Neptune. Before that, nobody knew of anything out beyond Neptune. And in the 40s and the 50s, two astronomers named Edgeworth and Kuiper was in the United States, speculated that the primordial solar nebula out of which the planets formed didn't have a sharp edge at Neptune. There's no reason to think that it ended abruptly at Neptune, that it would have tailed off beyond it. And it was likely that icy bodies condensed out of the nebula out there. Why icy? Because out that far, the sun is not hot enough to vaporize the ice, and it's left over and it forms objects. Okay, this belt of objects beyond Neptune now, if you go in the astronomical literature, it has a number of names. It's been called the Kuiper Belt, which is what I'm using in this talk, which contains Kuiper Belt objects. It's also known as the Edgeworth-Kuiper Belt, which contain Edgeworth-Kuiper objects. And it's sometimes referred to as the Trans-Neptunian Belt, which contains TNOs, Trans-Neptunian objects. In 1998, I say theoretical models of short period comet orbits suggest the evidence of a belt. And what does that mean? But before, we need to take a digression and talk about orbital elements before we can talk about theoretical models. Objects that orbit the sun orbit in ellipses, and there are 6 parameters that define the ellipse. And for this talk, I will be discussing 3. Okay, here's an ellipse. It's an orbit of something orbiting the sun. The sun is at the focus of the ellipse, and if you had a math class in high school, they described the focus of an ellipse. It's not the center. But there are 2 distances that measure from the center, and that's the semi-major axis, the half long length, and the semi-minor axis, which is called B. The interesting thing about orbits is that the period of the orbit depends only on A. So the Earth's A is 1 AU, 1 astronomical unit, 93 million miles, and an orbit at that distance has a period of 1 year. Kuiper Belt objects are out at 40 and 50 AUs. They have semi-major axes of that order, and those objects have orbits that range in the hundreds to thousands of years. What astronomers use is the eccentricity, which is the egg-shapedness of the ellipse. And if E is 0, then the ellipse is a circle. And the limiting case, as E approaches 1, you end up with a line. But an eccentricity of 0.99 is basically a very flat ellipse. We can define the perihelion distance, the closest that the object comes to the sun, which is A times 1 minus E, and the aphelion distance, the distance it is at its furthest, which is A times 1 plus E. So if E is 0 and it's a circle, then the perihelion and the aphelion distance are the same. If E approaches 1, then the perihelion distance can get very small, but the aphelion distance will be at most 2 times A. And the inclination I is the inclination of this plane to the plane of the solar system. That's shown in this figure, which is not so obvious. But if you think of a rectangle, whoops. What happened there? Sorry about that. Okay, if you think of the ecliptic plane as the plane of the Earth's orbit, and all the planets pretty much orbit in the ecliptic, and then you've got the plane of this orbit that you're interested in, which can be tipped with respect to the ecliptic. The angle of the tip is called the inclination, and it can range from 0 to 90 when the plane is perpendicular to the ecliptic, to 180 degrees when it flips over to the other side and the planet appears to be rotating backwards. Okay, here's a plot of inclination versus eccentricity for comets. And you will immediately notice that there seem to be 2 distinct pieces to it. There's all those objects near an eccentricity of 1, very high eccentricity, that have inclinations that range from 0 to 180. And then there's a bunch of stuff that can have a lower eccentricity, but by and large has inclinations that are small, 20 degrees at most. So what's going on here? Well, there are long period comets. All the comets with that have eccentricities over by 1, it's not plotted on here, but they all have very large A values. They're far away, and they're coming in on very eccentric and a random inclination. These are comets that are coming from what's called the Oort cloud. And in 1950 or so, a Dutch astronomer named Oort postulated that these comets had to be out there perhaps at 10,000 AU, or about a quarter of the way to the nearest star. And these are the long period comets. Okay, now what about the other stuff down there? Well, for a long time, it was believed that, well, you've got all these comets coming in from all directions, and as they come in, they'll go by and get perturbed or gravitationally affected by the big planets in the solar system, Jupiter, Saturn, and Neptune, and they'll get jostled. Some of them will get thrown out of the solar system altogether, but some will end up in the low eccentricity, smaller A, what we now call short period comets. And that was believed for a long time. And that's what it says at the top. But in 1988, computers finally got fast enough that we could test this. How do you test something like that? Well, you make a model of the solar system, in effect. You start with the planets at a given time, and you throw a comet in from the Oort cloud. And you say, okay, the comet has an orbit like the ones that are in that plot. And that, if you have the elements of the orbit, the equivalent to having the elements is knowing where the comet is at a given time and its velocity. So you know how fast it's moving and where it is. And you know where the planets are. And you say, okay, all the planets are pulling on this comet. And what force is the net force of all the comets? And where will, if it pulls on those comets, where will that comet be, say, in 24 hours? So you move the comet to where it will be in 24 hours. And then you say, okay, the planets have all moved in that time and they're all pulling again. Where we'll do the thing again? Where will everything be in 24 hours from now? And you do that 24 hours, 48 hours, whatever, 72, 96. And you keep that up and you do it for several million years. And you see where the comet ends up. Basically, what becomes of that comet over time. And can you end up, and then you do it for a couple of thousand of these comets, all different. Can you end up with a distribution of low inclination, short period comets? And the simulation, the quote in the paper that was written says, it appears to be impossible for the action of planetary perturbations, that's all those poles, on initially isotropic distribution of orbits, that's all the comets with all those inclinations that went from 0 to 180, to produce a distribution of visible comets with the observed inclination orbit. In short, you can't get the left side of the plot from the right side. That meant that these objects had to be coming in from an undiscovered source, which was already in the ecliptic and with low inclination, a previously undiscovered source. And that kicked off a number of searches, all of which were unsuccessful, which used photographic plates. And at that time, CCDs, the kind of camera that's in your digital phone, were starting to appear in astronomy, and they were being used, and nothing was found. But in 1992, they discovered what is now called the Kuiper Belt object, and it was given the designation 1992 QB1. And that's a preliminary designation given by the Minor Planet Center, and they're kind of weird. And if you want to know why, you can always ask me later. Okay, so how big an area to search? The rectangle in this field is the size on the sky of the field that Tombaugh used to discover Pluto. It's 180 square degrees. Okay, below it is a representative of how big the full moon is. So you can see that Tombaugh was searching immense areas of sky at a time compared to the full moon. The one below it is a typical CCD from the early 1990s. And of course, it doesn't even begin to cover the full moon. It's not even close. The box below that is how much squared area that was covered before they finally found something. So you had to cover something like that. The box below that is a field of view of what's called a mosaic CCD that we used in a search for Kuiper Belt objects that I'm going to talk about in a minute. And interestingly, it took about 2 of those to find 1 KBO. And that sort of matches the 2 times those sort of matches the box above it. And that seems to be the sort of area you got to search before you even find a KBO. The circle below that is for a telescope instrument that never got built, so we'll skip that. Okay, here's the orbit for QB1. You notice the orbit of Neptune is circular. Pluto, which is marked at the bottom, has a rather elliptical orbit. It comes inside of the orbit of Neptune. It goes out to almost 45 AU. I'm sorry, that's not 45. That's an angle. but it goes out to about 44 or so AU. And there's QB1, a circular orbit. The blue dotted line is 50 AU, so I guess Pluto goes almost out to 50. And QB1 is inside that. And it's not a perfect circle, but it's well outside of Neptune, and so it is a Kuiper Belt object. Okay, the survey we did with that mosaic camera I mentioned was called the Deep Ecliptic Survey. It was an early search for KBOs and Centaurs. Centaurs are objects that are inside of most of the KBOs. I'll talk about them in a little while. It began in 1998 at Kitt Peak Observatory, and in 2000 we added the Lowell International Observatory in Chile. They both have essentially identical telescopes, and the telescope at Kitt Peak is housed in the large dome in the picture. They used an 8K by 8K mosaic, CCD, and it's called a mosaic because it was comprised of 8 individual CCDs all pasted to the same substrate. And it was designed to maximize the rate that we discovered objects. The objectives were to determine the dimensions of the Kuiper Belt, the distribution of KBOs among various orbital classes, discover 500 KBOs and determine their orbits accurately. At the time we started this, there were only about 100 KBOs known. And facilitate physical studies with ground-based and space-based telescopes by providing a source of things that could be studied. This is the telescope at CTIO, and I always say that the southern sky is absolutely gorgeous. That's the southern Milky Way, of course, on the right. The 2 fuzzy patches on the left are the small Magellanic Clouds and the large Magellanic Cloud. They're satellite galaxies to our own galaxy, and they are only visible in the southern sky. This is the telescope we used. I don't know if this is the one at Kitt Peak or CTIO anymore, but they're essentially identical. It's a 4-meter telescope, and we were able to get a few nights every few months. This is the CCD. 2 of the CCDs are installed on the substrate, and you can get an idea of the physical size by the pliers in the upper left and upper right corner. So how did we observe? We took 4-minute exposures and moved the telescope to the next field while reading out the CCD. The cycle time result, it's about 5 minutes. We started by taking 2 exposures of the same field, separated by 2 hours, but we soon went to taking a 3rd exposure on an adjacent night. Why? Because we were getting a lot of false positives. If you have a 3rd exposure in the right place at the right time, it tells you that the 2 you got the night before were really a moving object that showed up on the 3rd image. And a good night, we got about 100 images. This is sort of the distribution on the sky. We went 6 degrees north and 6 degrees south of the ecliptic plane of the sky. Why haven't they all filled in? Well, we tried to avoid bright stars in the sky, which would bleed on the CCD and wipe out part of our viewing area. So these are fields that don't have bright stars in them. Okay, how do you find a KBO once you have the images? Every frame has thousands of stars in it. The Kuiper Belt objects and other objects, such as main belt asteroids, appear star-like. They don't wave at you and say, "Hey, I'm not a star. I'm an asteroid or a Kuiper Belt object." It's the same problem that was faced by Tombaugh with his glass photographic plates. And to do it, you blink the plates back and forth. Blinking means you superimpose the stars somehow, and then look first at the left star pattern and then at the right, back and forth. And the idea is that the stars don't move, and something that moved between the 2 exposures appears to hop back and forth. We also adapted something called color blinking, which I'll show you in a minute. Okay, so here's part of one. This is not even one whole CCD. This is part of a CCD. So as it happens, there are two moving objects in this field that I'm aware of, and I will blink them. In other words, I'll go to one and then the other. Let's see if I can do this reasonably. Yeah. Where am I going? Hang on. Yeah, I'm not sure where I'm going. I've gotten ahead of myself. I've gotten way ahead of myself. Sorry about that. Okay, here's the second frame of the pair. This one's identical to the first, except that a satellite came through. And if you blink them, and I can't do it. Take my word for it, I just can't manage it here. I will show you a different, let me back up again. This thing really hops. Okay, here's the color pair. Here's where we've color blinked. And down here, you can see what we do is the color blink, we load one image in the red plane of the screen, and we load the other image in the blue and cyan. And then we superimpose the stars. Red, blue, and cyan yield white. But if the object is not in both frames, then it shows up red in one frame and cyan in the other. So this is an object that moved from here to here. Now, the problem is that I know how fast objects move. Objects in the main belt, since they have shorter periods and are closer to the sun, move much faster than Kuiper Belt objects. And I know from experience that that one is typical of how fast a main belt asteroid moves. So that's not interesting from our point of view. But there's another one right there that moves about a tenth as much, and that's a Kuiper Belt object. That's the discovery of a Kuiper Belt object. If you blink the pair, you just get those two coming on and off left and right. Okay, why did we do this the way we did? Well, searching by human, we're using people, takes a lot of people time. And every field was examined in this process by two different people. What about using a computer? Well, the problem is that a computer for only 2 or 3 fields finds a lot of false positives. It links junk with other stuff and it's not real. And then you got to do something about it. You need to take at least 4 images per field to do a reasonable computer search. And even then, a human still has to look at the objects the computer finds because there are false positives. But we had limited time on the telescope and wanted to find as many new KBOs as possible. So we wanted to maximize the number of fields we did in a night, and that meant doing it by people power. And we had over a dozen people, astronomers, grad students, all kinds of people visually examining the data. Here's our collection of objects. These are the KBOs we discovered. And again, the blue dotted line is at 50 astronomical units, 50 times the Earth's distance. The orbit of Pluto is in there. And you can see that some are inside Neptune, some are outside Neptune. And but that's our haul. Okay, what are the orbits? Whoops. What do the orbits look like for these things? Well, again, I've drawn the 50 AU circle in red, and you can see the orbits are of all kinds of eccentricities, and some, like the one that goes off to the upper right, goes out quite a ways. It's got a very large A. The kicker here is that you may discover an object that has an A of 100 or 200, so that it has a very large semi-major axis, but you can't discover it at 200 AU. By the time most of these objects get out to 200 AU, there is no telescope on the Earth that can find them. So you discover them on their elliptical orbits closer in, and in 500 or 1,000 years, they may be out at 2, 3, 4, 500 AU, where they'll be invisible to people on the Earth. Okay, Deep Ecliptic survey finished in 2005. It discovered one short of our goal of 500. I think we did pretty well. At the time it completed, there were about 600 KBOs known. In the meantime, we've had 15 years since, other surveys have added to the count in the last 15 years, so there are now about 3,700 KBOs known. But of these, about 700 are lost. What do I mean by lost? They have ephemeris errors that are so large that they can't be recovered. If you say the object is there, plus or minus 20 degrees, which is a quarter of the way or a fifth of the way around the sky or something, there's no way you can point a telescope at it. So they may be found again in the future. And if so, and they're observed for a long enough time, that orbit can be linked back to the ones we observed, or the ones that have been lost, and they could be linked together. But for the moment, they're lost and they're not usable. Okay, the Deep Ecliptic survey, though, provided enough different KBOs that we were able to start classifying them into dynamical groups. The current groups that are used by astronomers are basically the same as those we found with the Deep Ecliptic survey. And now we come to the present. We've got 3,000 KBOs with good orbits. What have we learned in 28 years? Well, classifications. What you do is you do what you did, remember I said with the comets, that you integrate the orbit over time. The problem is that if you have an object, a real object this time, that has errors in its elements, in other words, if you know A, and say A is 40, but the error on that, the uncertainty to the measurement error is, say, 1 AU. Well, it could be 39, it could be 40, or it could be 41. And that's true of all 6 of the orbital elements, the 3 I mentioned and the other 3 that I'm not discussing now. So what you do is you take 2 clones, you sort of wiggle the errors a little bit and make what we call a clone, and you do a 10 million year integration at all 3. If all 3 behave exactly the same way, then the error is not going to make a lot of difference in what you classify this as, and you can define a class you believe in. If all 3 clones come out differently, well, then you better observe that object a bit more and improve the errors on its orbit. So there are now 5 classes of objects, all defined by how Neptune perturbed or didn't perturb a given object. First class, classical objects. These are objects which appear to have been mostly unperturbed by Neptune for the age of the solar system. That's the last 4.5 billion years. They all live near 43, 45, 46 AU. They have small eccentricities and inclinations. Over the years, classicals have been divided into those that really have small eccentricities and inclinations, and they're called cold classicals, and those have a slightly higher, and they're called hot classicals. Basically, they've been kicked a little bit. Then there are resonant objects. These are really strange. These are objects that do a dance with Neptune. Resonances are specified as 2 numbers, m:(n), and they have the property that m times the orbital period of Neptune is numerically the same as n times the orbital period of the object. What does that mean? Well, Pluto is in a 3-to-2 resonance with Neptune. That means if you multiply the orbit of the period of Neptune's orbit by 2, and the period of Pluto's orbit by 3, you get the same number. That's really weird, but there are. About 30 different resonances with Neptune have now been observed. How did they get into this weird dance? Well, it turns out that Neptune probably migrated outward very early in the solar system as it was forming. It started closer to the sun than it is now. And as those resonances, remember, they're a product of the period, which is a product of the period of Neptune, which in turn is a product of the size of Neptune's orbit. As the size of Neptune's orbits changed, the point of the 3-to-2 resonance, the distance that corresponds to, moves outward with Neptune. And as it passes over an object that's there, it tends to get captured into that resonance and stay there. Okay, then there are centaurs. I mentioned centaurs earlier. These are objects whose perihelion, closest to the sun, is between Jupiter and Neptune. They're inside of Neptune. They were perturbed inwards by Neptune, and now they cross the orbits of major planets. They may come close to Jupiter, Saturn, and Neptune. So their orbits are inherently unstable over time. Some will be perturbed out of the solar system. They'll get kicked away, and we'll never see them again. But some will be perturbed into orbits with perihelia closer to the sun. And this is how we get those short period comets in that plot I showed of the two types of comets. This is where they come from. Centaurs are essentially comets in waiting. I mentioned that the first centaur, which was given the designation, and after it given that funny designation like QB1, after an orbit is well known for an object, it's assigned a sequential number. And the first centaur was given the number 2060 and a name, Chiron. It was discovered in 77, well before the first KBO, but I'm calling it a KBO or KBO-like. In Greek mythology, Chiron was a centaur, and that name became the name of this class of objects. This object wasn't recognized as coming from the Kuiper Belt because the aphelion of its current orbit is also well inside the orbit of Neptune. So we discovered it, but we didn't know what it was. And then there are two more classes of objects that have been scattered outward from Neptune and have perihelia that are near or beyond Neptune. There are, and these names are very, very original, scattered near, those that have perihelia near Neptune, and scattered extended, which are also called detached, those would have perihelia that are at least 1 AU beyond Neptune and are not now affected by Neptune. They were kicked out, but they won't be affected again. Okay, here's a plot of the semi-major axis of KBOs versus their eccentricity. The red pairs of lines are about a dozen of the resonances. So there's a 1-to-1 resonance, a 5-to-4, a 4-to-3, the 3-to-2, which has a lot of objects in that particular resonance, a 5-to-3, a 7-to-4, a 2-to-1, and so forth. As I said, there are about 30, and there are 12 on this plot. Some of the 30 only have one member, and they're the ones in red. The interesting one here are also the 1-to-1. That means that the objects have the same period as Neptune. They're actually orbiting in the orbit of Neptune, and it turns out that gravitationally, 60 degrees ahead of a planet and 60 degrees behind a planet are stable, and you can have objects in that location that will stay there forever without being disturbed by the planet. So Jupiter has thousands of those, and they were given the name of Trojan asteroids. And I'm not going to go into why they were Trojans now, but that's a question you can ask later. These are so-called Neptune Trojans. The black dots are centaurs. They're the ones that come in inside of Neptune, but it's a little hard to tell from this plot. The orangish stuff is the classicals, low eccentricity between 43 and 45-ish, 44. The green are the scattered extended, the blue are scattered near. The reason that they go up to the right, the blue ones, for example, is that the only way we discover these objects at 75 AU, if you notice some of them are out, it's 50, 60, 70 AU. The only reason we discover these is because they do have large eccentricities. If there are ones with small eccentricities out there, they're too far away to be discovered and we won't find them. Okay, here's the same plot, but now on a log plot. So this is the ticks on the bottom are 10 AU, 100 AU, and 1,000 AU. And you see there are objects that have semi-major axes that go out at least to 1,000 AU, as large as 1,000 AU. On this plot, I plotted the perihelion versus the semi-major axis. This one, you can see why the Centaurs are Centaurs. You'll notice all the black dots are below 30 AU. They're the ones that come in closer than Neptune. The resonances are about in the same place. The classicals are, but now you can see that the blue objects, the scattered near, are all a little closer to 30 AU, which is where Neptune is, than the green ones, which are scattered extended. Okay, well, what else can we learn about KBOs? Well, we can learn something about their shapes. As we do with main belt objects, we can measure the light reflected from a Kuiper Belt object as a function of time and generate what's called the light curve. How does this thing vary over time? Those objects with small amplitude light curves are roundish. Think of a rotating beach ball, well, a uniformly colored beach ball. As it turns, the amount of surface you see is the same no matter how it rotates. So the light is not going to vary as the object rotates. On the other hand, if you have something like a football, when it rotates point onto you, it's got a smaller cross section than when it's the long way around. So you get this versus that. And those will have larger amplitude light curves and will be elongated. The problem here, of course, is that KBOs are much fainter than main belt asteroids. So the only way to do this, and the only way to do almost all KBO science, is on a big telescope. Here's a light curve. So this one varies by, the number on the left is a magnitude. That's what astronomers use to measure brightness. the orbital period, the turning period, the rotational period, is given as phase rather than hours. So the phase goes from 0 to 1 when it comes back to where it was. So this plot shows two rotations, so that everything at 1.5 is the same as 0.5. And you'll notice, for instance, the second bump around 0.6, all the dots are duplicated out at 1.6. So there's two rotations in the object. Okay, it turns out that Kuiper Belt objects have little objects orbiting them. They have moons. And they have satellites, you have primaries and satellites, and you have binary KBOs. And what's the difference? Well, a satellite is considered to be a small object orbiting a somewhat larger object. Just for grins, and it's not official, say the system is a primary satellite system. If the center of mass of the system, that's the balance point between the two objects, is inside the larger object. So if you have a very big object and a little object orbiting it, the center of mass is within the big object. All of the 6 largest KBOs have satellites. A binary object is different. It's two similar mass objects orbiting each other, such the center of mass lies between the two objects. And we know of about 100 binary KBOs. That's surprising. You wouldn't expect them to form in pairs, but they do. Pluto is an odd case. It has 4 small satellites, which are where the center of mass is inside Pluto, and a very large satellite, which is actually makes a binary pair. Pluto's largest satellite is half the size of Pluto, and it's called Charon. So Pluto and Charon are a binary system. The center of mass is well outside of Pluto. And after the New Horizons flyby of the one KBO we've ever gotten a picture of, the one that was used in the ad for this talk, we now know there's at least one contact binary in the Kuiper Belt. That's a binary with the two objects, which are, in this case, fairly similar in size, are actually physically touching one another. And there is indirect evidence from light curves, like the one I showed earlier, that there are more. We think there may be another half dozen objects in the Kuiper Belt that are contact binaries, maybe 8. But we don't know, we won't be able to tell until we get a picture of them. And we can't do that from the Earth, unfortunately. So what's the good of a satellite? Given an object with a satellite or a binary pair, we could measure the size of the orbit. And if we can measure the period, it turns out there's a magic formula found by Kepler in the 1600s that relates the size of the orbit and the period to the total system mass. We can actually measure, we can weigh the system in effect. If we can then determine a size, maybe by occultation, and my last talk to this forum was on occultations. It's on the web if you want to learn about occultations. Then we can determine the density, because the mass over the radius cubed is the density. And we can determine if it's got a density of 1, then it's an ice cube. If it's got a density of 4 or 5, then it's a rock. So you can actually get physical information about these objects from a satellite and from an occultation of the same object. Here's an orbit superimposed showing a smaller, fainter object orbiting a brighter object. And it looks like the orbit goes, let's see, July. So it's got a period of maybe a year. This is a Hubble picture, by the way. Now we come to a question. It's been in the news lately that there is a planet X or planet 10 or whatever you want to call it, lurking out there. That we have an undiscovered object that may be bigger than the Earth. What's that all about? Well, if you take the perihelia, the orbits, and plot the perihelia of objects that have semi-major axes greater than 250 AU, they appear to be aligned. Ignore the left plot. I stole this from a paper, and I couldn't get the right plot out. I'm only interested in the right-hand one. Here's all the orbits of the half dozen or 8 or so objects with 250 AU or greater semi-major axis. The perihelia all sort of point in the same direction. If you look where they're pointing, that's the arrows. They're sort of pointing in the same general location, off to the right. Why aren't they randomly oriented? Well, it turns out this has a small chance of happening randomly. I mean, if you place them randomly, you'd expect them all 7 to be pointed, one there, one there, one there, one there. Why are they all pointed there, at least within a narrow cone? Well, a mathematical study was done by astronomers at Caltech, and they find that the alignment could be caused by an object about 5 times the mass of the Earth. That doesn't mean it is, it could be. Its orbit would have an eccentricity of about 0.15 to 0.3. It would have a semi-major axis out at 400 AU. And since the eccentricity isn't very big, it would never get much closer than, say, 200 AU. Does it really exist? Oh, at an inclination of about 20 degrees, so it would be in the plane of the solar system. Does it really exist? Nobody knows. I don't know. There have been searches. Actually, one of the astronomers at the university here in Flagstaff at Northern Arizona University has done searches for it and has found nada. That doesn't mean it doesn't exist. It may exist. At this point, it's just an interesting conjecture. The problem is, even 5 times the mass of the Earth at 400 AU, it would be exceedingly faint and very hard to find and moving very slowly. So, don't sit up waiting for it. And now we come to Pluto. And there's been a fair bit of controversy. When I do meet an astronomer live, which I can't do right now because of COVID, I do this up at the Giovanni Open Deck Observatory, and I talk to people live, and we bring objects in the sky up on the TV screen. And the question I invariably get is Pluto a planet? And Gerard Van Bell, as I said, will be discussing this next week from the prospect of having been at the IAU meeting live himself. So you could get his viewpoint on this too. Well, should Pluto be a planet? How did we get here? And what in the world is a planet anyway? Well, clearly Pluto is a Kuiper Belt object. I'm not going to argue with that. It's in a 3-to-2 resonance with Neptune, just like a lot of other KBOs. And by the way, I did mention it earlier, a 3-to-2 resonance or another resonance means that an object in the resonance never gets very close to the object it's in resonance with. If Pluto were not in a 3-to-2 resonance, by now it might have been kicked out of the solar system and become an extended object, just like the extended objects. So the resonance protects it. Okay. In 2005, astronomers at Caltech, in fact, the same astronomer who was involved with this large object, Mike Brown, discovered a new KBO in images they had taken in 2003. Apparently, it had sat around for 2 years and nobody noticed. This object was given the designation, and here's another funny designation, 2003 UB313, and was later named Eris. It's since been given a number, and I offhand don't remember what the number is. From its brightness as seen as the Earth, and its known distance from the Earth and the Sun, we could assume, and there's an assumption here, a reasonable albedo. What's an albedo? It's the amount of light that the object reflects. What's a reasonable albedo? 20 to 40%. Dirt, concrete, that's sort of in that range. And we could work backwards and derive a size. And when that was done, it turned out that Eris was thought to be bigger than Pluto. Aha, if Pluto's a planet, Eris is a planet. So was Eris the 10th planet? And that's what kicked off all this discussion about planets. Well, Eris started a significant amount of discussion about this. Some astronomers, some of whom had big mouthpieces, like Neil deGrasse Tyson and Mike Brown, who actually discovered Eris, objected to calling Eris and Pluto planets, and maybe even Ceres and Vesta. Were they planets too? They said no, only 8. Others felt that they all should be planets. Well, if Eris and Pluto are, why aren't Ceres and Vesta? They're not that much different. The IAU, the International Astronomical Union, which is the official hoo-ha arbiter of definitions in astronomy, formed a committee to decide. And at the 2006 meeting of the IAU, August 14th to 25th, the committee released its recommendations on the 16th. This is during the meeting. They were, A planet is round. It turns out it takes an object about 400 or 500 miles in diameter to have enough gravity to pull itself into a round shape. Objects smaller than that are lumpy and are not round. B, a planet orbits our sun or another star. Reasonable. And C, a planet is not a star or a satellite. So it's not a self-luminous object, and it's not an object orbiting another object. This definition was approved by the executive committee, and this is a mouthful, of the Division of Planetary Sciences of the American Astronomical Society. At the time, I don't think the Europeans had formed a planetary society. They have one now, but the DPS was the planetary society of the world. I've been a member of the DPS for the past 50 years, 45 years. But it was not approved by the general membership, only by the executive committee. It wasn't time. They announced this right at the start of the IAU. So what happened? Well, it's very unclear what happened. But in the next week, the IAU managed to convene a number of small groups that changed the recommendations, rechanged their recommendation, changed it again several times until the proposal that was actually voted on became a planet is round, that's the same. A planet orbits the sun, that changed, it's only the sun. And C, a planet has cleared the zone in its neighborhood. The proposal was voted on and passed by the IAU members who attended a meeting set up on August 24th for that vote. Now, we get to my opinion. I am a planetary astronomer at Lowell Observatory, where Pluto was discovered, but Lowell, for practical reasons, has decided as an observatory that it will not have a position on this. However, I certainly can have an opinion on this, and I have a very strong opinion on this. In my humble opinion, what's wrong with what the IAU did? And from that, you can tell what my opinion is going to be. One, the vote was taken by the members who were present on the very last day of an 11-day meeting. 400 people voted out of an IAU membership of 9,000. Two, very few planetary astronomers usually attend the IAU. The IAU is comprised very highly by stellar and galactic astronomers. They do very little planetary astronomy discussions at the IAU. Planetary astronomers don't generally go. And the DPS or its membership was never asked about the revisions. Remember, they approved the first definition, but they never got a chance to say something about the second. Planets are defined as those orbiting the sun. No mention of objects orbiting other stars. We know of thousands of objects that orbit other stars. The planetary astronomers are happy to discuss these things at their meeting and call them planets. So we have sessions on exoplanets and planets going around other stars. But as far as the IAU is concerned, they're not planets. The IAU calls them exoworlds. Why? Because it's the IAU. The resolution specifies that Pluto specifically is not a planet, but that it is a dwarf planet. But the word dwarf doesn't modify the word planet. If it modified the word planet, then it would be a planet. So dwarf cannot modify planet because Pluto isn't a planet. But dwarf stars are small stars, the IAU's definition. Dwarf galaxies, IAU's definition, are small galaxies. But a dwarf planet is not a small planet, since Pluto is explicitly not a planet. I like to say when I do this, the dwarf planet, you have to remove the space between dwarf and planet and make one word, a new object called dwarf planet. Clearing the neighborhood is not a particularly clear and easily understood definition. Planets are the most fundamental thing in our solar system, and they're defined by a definition that nobody except a mathematician can understand. Also, there are tens of thousands of asteroids that pass near the Earth. Has the Earth cleared its neighborhood? You could argue that maybe it hasn't. And if we were to discover an Earth-sized object out at 50 AU, it would fail the mathematics that go into this, and it wouldn't be a planet. So you could have a planet at 1 AU, called the Earth, and another object exactly the same size at 50 AU, it would not be a planet. That's crazy. I said logically inconsistent, but it's crazy. Okay. Most, but not all, there are a few diehards. Planetary astronomers would prefer the original definition. Round, orbits the sun or a star, and is not itself, I've got a typo there, a star or a satellite. That would mean that there's probably 15 or 20 known planets in our solar system. So what? You know, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Pluto, Eris, Haumea, Ceres, Vesta, big deal. Some are rocky planets, some are gaseous planets, some are rocky dwarf planets. Ceres and Vesta would be rocky dwarf planets. Some are icy dwarf planets. Eris, Pluto would be icy dwarf planets. Big deal. There was an argument at one point complaining that kids would not be able to remember the names of all the planets. Oh, well, so what? I can't remember the names of all the flowers, but I can still call them flowers. There's a PS to all this. It turns out that the size of Eris was later accurately measured using an occultation, which is a very precise way of measuring the size. You can then go backwards. Once you have the size, you can determine the albedo. How bright is it? It turns out that the reasonable albedo that was guessed for Eris was wrong. Eris reflects 96% of the light that hits it, and as a result is somewhat smaller than the guess that started all this. So if we had known the albedo in the first place, this might never have come up. Anyway, 96% is like a freshly fallen snow. It's exceedingly bright. It's the brightest object we know of in the solar system. So now Pluto is still the largest object in the Kuiper Belt, and we're dealing with the results of this estimation still. And I think that's it. Thank you. We can take some questions. Let's see what we got here. All I have to do is move the chat window over. Somebody asked, is this something that LDT can be used for? Yes, I use LDT to measure positions of Kuiper Belt objects to keep them from becoming lost. There are studies of light curves of Kuiper Belt objects with the LDT. The LDT is the Lowell Discovery Telescope, for those who don't know. It's Lowell's largest telescope. It's a 4.3 meter telescope, the 5th largest telescope in the continental United States, and it's all ours. So yes, and the light curves that I mentioned that indicate that some objects are contact binaries are done by an astronomer here at Lowell and using the LDT. So yes, you could use the LDT. You certainly can and do. Question, Jupiter has been hit a few times since Shoemaker leaving 9. So why is it a planet? Well, I suppose you could make the argument that Jupiter clears most of the stuff in its orbit. But, you know, this is a mathematical definition, not a truly absolute practical definition. Is there enough time, size, given the size and distance from the sun? The mathematics of this are very complicated, and I find this difficult to make sense out of. Are there differences in composition for different regions of the Kuiper Belt? Do we expect there to be differences in compositions between KBOs and Oort cloud comets? So Eris is probably a large ice ball with a clean surface. Yeah, it probably is. And yes, there are compositional differences. You can measure, one of the other things you can measure about Kuiper Belt objects is their color. In other words, do they reflect more light in the red than in the blue region of the spectrum? And yes, some Kuiper Belt objects are reddish, some are not. So there are differences in composition that we don't fully understand. Are space-based telescopes used for KBO surveys? Well, obviously one space-based telescope is New Horizons, and it's been used to study Pluto and what they called Ultima Thule, which was a made-up name. It's now been given the official name of Arakoth, and it was certainly used to study that object. And the Hubble Space Telescope is used to do binary work because you need to separate the two objects, so you need the resolution, except for the very widest Kuiper Belt binaries. They all have to be done with Hubble. So yes, Hubble and other space-based telescopes are used for KBOs. Any other questions? I think we're done. And as I said, if you're interested in occultations, somewhere out there on the Lowell website is a talk I did on occultations. Thank you.